Hi folks, Mr. G here. Welcome back to HSS Engineering. Today we're going to be going over problem number 2 on how to solve trusses using the method of joints. So we reviewed problem number 1 the other day. We kind of did an intro video on introducing you to all of the components of how to solve a truss, all of the letters and what they mean and how to use them, and then we went into solving truss number 1. So all of this is a technical application of all of the trigonometry you've already learned in school. You definitely have spent some time doing trig in your times as a human so far, and in the real world this is how you apply it. These are the kind of problems that engineers are going to be looking at. Now, engineers are going to be using definitely like computer-aided drafting and programming, and all sorts of other factors are going to kind of go into the final solution to what problem you're working on as a structural or civil engineer. But understanding kind of how the forces work, how the math works to get there, will just deepen your understanding so much more. So all of the problems that we're kind of going through are relatively simple problems, but you need patience, you need a sharp pencil, some paper, and just take it step by step by step. And I would recommend that this kind of cheat sheet right here, you make yourself one of these, or I can even print you a copy if you'd like. So if we remember our trigonometry, sine of theta is equal opposite over hypotenuse, cosine of theta is adjacent over hypotenuse, and the tangent of theta is opposite over adjacent. So that's our trigonometry that we're going to be using, mostly the sine and cosine. We've got our terms. Again, capital sigma stands for sum, so if you see the sum of something. M is a moment of force measured in Newton meters. R is the opposing reaction at a support. V is the vertical forces, so all the forces acting down on the truss. So this would be a vertical force. So usually you'd see something like the sum of all of the vertical forces. H is the horizontal forces, so in this case we have this way. F is the force acting in a member. So F is what we're trying to find for each member. As you can see in this problem, we want member AB, AE, BC, so all the different members. So F, force in a member, and that's measured in newtons. Okay, so if we have forces acting in the horizontal and vertical direction, once again, we create a moment. So a moment is a turning or rotational effect of a force calculated as force multiplied by distance. Now in our last problem, we didn't really have a whole lot to go on with the distance. Let me see if I can bring it up here. We only had angles, and we had to make some assumptions about the distance. And if it's parametric, and parametric means if everything gets equally larger together, if we assumed that x is equal to 1, we could figure out the rest of the truss. On this one, we actually have a measurement to go off of. We have a measurement, and we have some angles. So we could maybe figure out a little bit more. So that's how to calculate a moment. If we keep going down, we want to also make sure our truss is always in equilibrium, because otherwise our calculations are wrong. We need to make sure the sum of the moments and the sum of the horizontal forces and the sum of the vertical forces always must equal 0. And then our truss is balanced. It works. Newton's third law. Every action must have an equal and opposing reaction. So if gravity or a weight is pulling down in the center of a truss, for example, this 50 kilonewtons here, there also must be an equal and opposite reaction of 50 kilonewtons pushing up through the supports. So we just keep that in mind and we go from there. All right, I'm gonna move my cheat sheet to the side so we can start working on this problem. Okay, always good to draw stuff and start with what we know. So we have, let's start by putting in some arrows to help us really understand what's going on here. Okay, so we have a rolling support right here. So we are going to have an opposing arrow that is going to be our reaction at support D. So that's our RD. We are also going to have the vertical forces acting upon node number A, or point number A. So we have the vertical forces acting on A. We also have, if we turn it this way, the horizontal forces acting on A. So that's going to be A, horizontal. Okay, we've got our AH, our AB, and our RD. Okay, so we calculate the moments. So we know that the sum of the moments acting on point D are going to equal to 0. So we can boil that down to, so we have 3 horizontal members. We have 3 horizontal members. So if we have 3 members that are spanning from point A, and they are being pulled on in the vertical direction, 3A, B. And we have 50 kilonewtons. That is going to be pulling on specifically one of the nodes, times 1. This must be equal to, if our moment is to equal to 0, this must be equal to our 80 kilonewtons acting in the horizontal direction. So our 80 acting in the horizontal direction, multiplied by our height, which is 0.75. 0.75. If we grab out our handy dandy calculator, I just had to go and find it. I go boop, 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 boop. You will find that if you evaluate this expression, that will give us AV. So the vertical forces acting on A are going to equal to 3.33, repeating just like 3.3333 forever. 2 decimal points is good. Kilonewtons. Kilonewtons. Lovely. Okay, now we're going to look at the forces acting in the horizontal direction. So we know that we've got our vertical forces acting on point A. Lovely. We could fill that in here. It's equal to 3.33 kilonewtons. Now we need our horizontal direction. So we have the sum of the forces acting in the horizontal direction is going to equal to 0. So that gives us AH is equal to 80 kilonewtons. Okay, so we only have one force acting in response. We only have one member up and down. It's a basically equal and opposite reaction. There's not a whole lot to figure out there. That's just the answer. That's our horizontal direction. So it needs to oppose equal and opposite. So our AH is going to equal to 80 kilonewtons. Okay, moving on. We have next the sum of the moments acting on point A now. So we did point D before, we got 3.33. We need the sum of the moments acting on point A. So sum of the moments acting on point A. And those are going to equal to, you guessed it, 0. All right, so we have, once again, 3 different members in the horizontal direction. So we've got 3 horizontal members that are going to be providing like downward force into RD. So we've got 3 RD. Is going to be equal to, so we've got 50 kilonewtons so this time it's a little bit different because the last time we were from point D, we were only 1 member away, and this time we are 2 members away. So 50 multiplied by 2 members away instead of multiplied by 1 member away. We need to add that to our 80 kilonewtons in the horizontal direction multiplied by that 0.75. All right, and that will give us our RD is equal to, if you go in your calculator, RD is going to be equal to 53.33, forever repeating, kilonewtons. Okay. Which, if you're paying attention here, we kind of did a really roundabout way to solve that. Once you solve for one, it's pretty easy to figure out the other one on a simple truss like this. So we have 50 kilonewtons coming down vertically through this node. And we determined that there is a force of 3.333 kilonewtons acting down into A. And we also just determined that we've got 53.33 kilonewtons acting up into our rolling joint D. And if we want to check that this is right, we've got 53.33. If we minus away 3.33 kilonewtons, that gives us our magical number of our forces in the vertical direction. Woo! Because it needs to be equal and opposite. So I'm going to type this in here. It is equal to 53.33 repeating kilonewtons. So we check this. We know it's right. It makes sense. Make sure every time that you do a force equation, like, bring it back to the basics. You have all the forces in the horizontal direction equal 0. All the forces in the vertical direction equals 0. All of the sum of the moments around both of the points need to equal 0. So we're golden. All right, now we can start figuring out all of the forces in each individual, or acting off of each individual joint. So last video I did this, I probably didn't do the best job of describing it. So I'm gonna try and do better this time to give you a better understanding. I'm new to making these videos and it'll get smoother over time. Last time I saved drawing everything for the very end, but why don't we draw it together right at the start this time? So we're gonna start by looking at joint A right here. And so let's draw a little picture of it. So we have a solid joint. It's not moving anywhere, it's secured. And we know that acting downwards, we have, on joint A, forces in the vertical direction are going to equal to 3.33 kilonewtons. We also know that we have forces acting in the horizontal direction at point A, horizontal direction, that are going to equal to 80 kilonewtons. 80 kilonewtons. We are going to have a member that spans up. We are going to have a member that spans out. And we actually, ooh, that's cool. We have a 3, 4, 5 triangle. How did we determine that we have a 3, 4, 5 triangle? Well, let me tell you. We have 1 meter on the bottom. If we go up this way, we have 0.75 meters. So that means that this is 3 out of 4 if we turn this into quarters. 0.75 is 3/4 of a whole. 1 is 1/1 of a whole. And if we have a 3 and a 4, that means, what we know about Pythagorean theorem, we must have a 5. So this is so great. This makes our lives way easier. We have, boom, a 3, 4, 5 triangle. Okay, this member is FAB, because this is point A, and up here is point B. This member is FAE, and now we have a little picture to go to. I don't think I'm missing anything. Nope, that's good. Okay, so what shall we start with, vertical or horizontal? Let's do vertical. Let's do vertical. I'm feeling vertical. So we have the sum of the forces in the vertical direction must equal, haha, you guessed it, 0, 0, 0, 0. Love 0. And hold up, weed whacker, it's so loud. Let's wait for it. Okay, weed whacker's gone. We can get back to it. Okay, so seeing as we have a 3, 4, 5 triangle, we can actually not even do trigonometry to start this problem. So if we know that we have a 3, 4, 5, and all the forces vertically, sum of the forces vertically equals 0, this FAB, if we take 3/5 of this FAB, that is going to equal to our forces acting vertically in this direction on point A. So we could do 3/5 FAB is equal to 3.33 kilonewtons. Newtons. All right. And if we get our calculator, type it in there, if we reduce this, that means FAB. So the forces acting in this member are going to equal to 5.56 kilonewtons in tension. Boom. Get that little arrow in there, in tension. Pulling apart. We should also have a little arrow in there. All right. Wonderful. Okay, let's look at the forces horizontally now. So, okay, so we've got the sum of the forces in the horizontal direction are equal to 0. So we're looking at that FAE section here. So now, kind of similarly, if we have FAB figured out, we can pretty easily use this 3, 4, 5 triangle once again to determine the reaction in the horizontal direction. So if we have the forces FAE, the force is acting on this member, and we add it to 4/5, because we've already figured out the vertical direction. So 4/5 of FAB needs to equal to the equal and opposite reaction of that 80 kilonewtons that we have. So that's going to equal to 80. So we know from the last one that if we switch the terms here, if we've got FAE and we add 4/5 of FAB, we figured out FAB. FAB is 5.56 kilonewtons. 5.56 kilonewtons. That's going to equal 80. And if we down into our calculator, that will give us FAE. Oh my goodness. So many interruptions. Never going to get this video done. Eventually. Here we go. FAE is equal to, I'll scream over the bell, 75.56 kilonewtons in tension. Dun-dun. Okay, I'm going to pause the video. We'll finish this later. But we have two things that we can write in here. We're so happy. We have FAB. So the forces acting on member AB is 5.56 kilonewtons. We have the forces acting in AE, which is 75.56. 75.56
This is an announcement for all
kilonewtons.
those on the soccer team. Please know that there is a
I swear, this is the noisiest place in the world. I keep having to pause the video. Okay, so, and we know that both of these are in tension. Tension. And if you want to get crazy, I'd encourage you to add these two together and see what you get. And yeah, should bring you to your double check to make sure it opposes the forces properly. All right, well, pause, catch you later. Alrighty folks, sorry about that. Bell went and ran out of time. I'm back, new shirt, new day. Let's see where we left off here. Okay, so we just finished looking at all of the forces in the members that connect to joint A. So we've got our little diagram of joint A there, which we have FAB, which is over here, and FAE. Both of these members are being forces applied on them in tension. So tension is when things are being pulled apart. So that's how this structure is working. So let's move on to the next one. A, why don't we go to B next? Let's go to B, that one right there. Okay, at joint B. Joint B. Okay, you're gonna get bored of me saying this, but you know what's coming. All of the forces, the sum of the forces rather, acting, sure, let's go in the horizontal direction first, must equal to 0. Okay, so let's do our little drawing again. Again, in the first problem I did the drawings afterwards. I think it'll be helpful to you to do them first. So we've got our little joint B right there. Call that B. And we'll have an arrow going down, a little arrow guy. We will have, actually, this one, if we think about how these will all be, the forces acting upon them logically, this one will actually be in compression, so that will split the other way. And this one will be in tension. Okay, 1, 2, 3. And what do we know so far? We know that FAB is equal to 5.56 kilonewtons. And what else do we know? Well, this is FBC. We're going to try and figure that out next. BC. And FBE. FBE. That's BE and BC. Those two right there. Outside of that, what else do we know? We know that this is a 3, 4, 5 triangle. It's going to be very helpful for us. It already has been. It takes away some of the trigonometry and just we can calculate it. Super easy. Love 3, 4, 5 triangles. Okay. Yes. So some of the forces in the horizontal direction must be equal to 0. So let's take FBC first. So if we take FBC, we know that if we are looking at our 3, 4, 5 triangle, that because FAB is going on the 5 direction of that 3, 4, 5 triangle, that that 4/5 of FAB is going to be equal to FBC. Let's see how that works here. We've got FBC, the forces are going horizontally this way. So if we take 4/5 for the forces going this way, it's going to equal the forces going that way. So if we do a substitution for FAB, because we know that already, we've got FBC is equal to 4/5 multiplied by 5.56 kilonewtons. Okay. And where did my calculator go? I love to do this for the video. Okay. We do all the calculations, put that in. That gives us FBC is equal to 4.45 kilonewtons in, which way is it pulling? In tension. Tension. Lovely. All right, we can go ahead and throw that in there. FBC got 4.45 kilonewtons in tension. Okay. Keep moving on. Let's do our vertical forces now. So those are our horizontal forces. We've got the sum of the forces vertically must equal to 0. So now we've got FBE. FBE is going to be equal to 3/5 of FAB. Why is this? Why is this? Why do we have 3/5 FAB? Well, the same way, because we were calculating this one before, and it was 4/5, was that opposite over hypotenuse? This time we have, calculating FBE, we have adjacent over hypotenuse. That's 3/5. So 3/5 FAB, those will equal, and we know FAB, so we can do FBE is equal to 3/5 times 5.56 kilonewtons, which means FBE is equal to 3.34 kilonewtons in the opposite direction, in compression. That way. Compression. Lovely. Okay, we can write that down. 3.34 kilonewtons in compression. Okay. Now we can go to our next joint. Why don't we do, I don't know, we've done A, we've done B. Let's do joint E. Joint E next. We'll see if we could fit this on this page. At joint E. Give it some underlines there. Beautious. Okay. So, you know I like my little drawings. Let's do a little drawing. We've got a point E, which we'll write down point E right there. We have a force going this way, which is going to be the force on EF. EF. We've got the force going this way, which is going to be actually pushing down in, because this one's posing this way, that one's posing that way. Going to be squished in that compression, 3.34 in compression. 3.34 kilonewtons, and that is FBE. We've got the AE, which is going to be going this way, and we know that that is 75.56 kilonewtons, and that is AE, FAE. And then we have this other one coming out sideways, right this way. And that's going to be, again, in compression. Just by looking at it, we can see that that will be squished. Okay, and this, let's see, we've got EC. So the force is acting on EC. And once again, we don't know. What we do know is that we have a bunch of 3, 4, 5 triangles. So if we put it in here, that is a 3, that is a 4, and that is a 5. Wow. Cool. Okay, we've got our little diagram. Lovely. Let's look at the forces in joint E. Okay, if you don't know how to guess the equation by now, I'm going to be very, very sad. The sum of the forces horizontally, the sum of the forces horizontally is going to be equal to 0. So, we have the sum, or sorry, the forces in the EF direction. Forces in the EF direction plus four-fifths of the forces in the CE direction, or EC direction, sorry. EC, I should actually write that properly. That should be CE, based on the alphabet. CE. A, B, C, D, E. CE. 4/5 CE. Let's erase that better. Is going to be equal to FAE. FAE. Why is that? Why did we get FAE? Okay, so the sum of the forces. We have a force acting this way. We have a force acting this way. We don't know either of these forces. We have a force acting this way. So the sum of the forces, they're pulling, they need to be equal and opposite. So They're all acting in opposing ways, obviously. We know this one, so we can substitute that in. So we've got FAE, it's going to be 75.56 kilonewtons. Okay, so we've got this filled out, and we know that it needs to be 4/5 CE, which there should be a number in here. And this is where I've run into an issue of, okay, I'm stuck. I don't know the forces acting in EF, and I don't know the forces acting in CE yet, because I need one of them to calculate the other one. Because both of these are unknown, I can't use the 3, 4, 5 triangle here. It's kind of useless to me. I need to use the forces in FBE and FAE first in order to calculate this one. So I'm going to put a pause on that. And we're going to start looking at the forces in the vertical direction. Sorry for leading you astray here. Okay, so we have the sum of the forces in the horizontal direction. We're going to fill in this number in a second. But we need to figure out the sum of the forces in the vertical direction, which equals 0. Okay. If we have FCE is what we're trying to figure out here. FCE. So we have, let's see here, FCE, that is going to be 3/5. Yes. So from here, we've got 3, so we got that opposite over that hypotenuse. So 3/5 FCE. So we've got 3/5 FCE is going to be equal to FAE. So this guy over here. Because we know on this side, we don't know this direction. So that's going to be 3/5 because we know the 4. So 3/5 FCE is going to be equal to FAE. What do we know already? FAE. So we've got 3/5 FCE. It's going to be equal to 3.34 kilonewtons. Okay, grab our calculator. We have FCE all by itself is going to be equal to 5.57 kilonewtons. Okay, boom. We've got CE equals 5.57 kilonewtons. We could directly take that 5.57 and throw it up there. And then we can go and do our calculation. Type it in there. We have the forces acting on EF. FEF is going to equal to 71.11 kilonewtons in tension. And this one down here is also in tension. Yeah. Because we've got the force in CE is pulling that way. The force in EF is going that way. It's being pulled apart. Let's add these in here. So we have FCE. FCE. This one, 5.57. 5.57 kilonewtons in tension. And then we've got FE. EF. Oh, I wrote this backwards on my sheet here. Uh-oh. Okay. Let's do joint F now. Joint F. That would be a good one to do next. Okay. At joint F. All right. might start to do these a little bit quicker. I'm hoping you're catching on by now, and the video's already been 40 minutes. Time flies when you're having fun, right? Oh, there's the bell. Hang on. Okay, announcements are done. We're back. All right, so sum of the forces vertically is equal to 0. Which, this one's super easy. If we're looking at the forces acting on CF right here, we have 50 kilonewtons pulling down, which means we have 50 kilonewtons in tension pulling the other way, which is equal to 50 kilonewtons in tension. Oh, before I get carried away, let's draw our little diagram. We'll go nice and tall there. I wish I was better at art. There we go. Got that one, got that one, got that one. We have a force of 50 kilonewtons going down that way. We know that the forces acting in FE, or EF, whatever, are equal to 71.11? Hold up. Do we know that? Oh yes, that's the last thing we figured out. I forgot to write that down on my sheet here. So we had EF, or FE, is going to equal to 71.11 kilonewtons in tension. Okay. And what else did we figure out? We did CE. Yeah, and now we're figuring out CF. Okay, we're golden. So yeah, so FE is 71.11. What else do we know? We don't know a whole lot, other than this is the forces acting in CF, which we know now. CF, we just figured that out. It's 50 kilonewtons, so we can write that down. 50 kilonewtons in tension. A lot of tension on this truss here. And then we know that this is the forces acting on DF. DF, right there. So now we've got our little diagram. We're off to the races. So we'll do the sum of the forces in horizontal direction are equal to 0. The forces acting on DF, this guy right here, DF, are equal to the forces working on FE. So again, super simple, because we have an equal and opposite reaction. There's no other sideways members acting on this one. So the forces acting on FE, which we know the force is acting on FE, so F dF is going to equal to 71.11 kilonewtons in tension. I should write that down. Tension. See how that works? Pulls that way, and you equal and opposite force to go that way. So that is dF. So we have 71.11 kilonewtons in tension. We are down to our last one. We are so close. Okay, we just have at joint C left. At joint C. So we're going to do at joint C. Could probably do this from at joint D as well. That would work, but I'm going to do joint C for funsies. Yeah. Okay, diagram time. We have our point C that's right there, and we have a member going down this way. We have a member going down that way. We have a member going straight down. We have a member going out. This is just a wild time. And we have a force acting this way, which is 80 kilonewtons. we have FBC is right there, which we know is 4.45 kilonewtons. We have FCE, which is right here, which we know is 5.57 kilonewtons. And we know that this right here is a 3, 4, 5 triangle. And we know that the opposite of that is also a 3, 4, 5 triangle. This is going to be FCD. And this right here is going to be pointing that way. This one's going to be pointing that way. It's going to be pointing that way. All the ones in compression versus tension. This one is going to be pointing the opposite direction. So FCD, that's the only one we need to figure out. Oh, we also know that this is FCF, which is equal to 50 kilonewtons. So we have most of the information already here. I'm actually going to draw this triangle for us too. 3, 4, 5. Beautiful. Okay, 3, 4, 5, 3, 4, 5, 3, 4, 5. Beautious. Okay, so this might be the most complex one to figure out because there's so much going on here. But let's break it down. The sum of the forces in the horizontal direction must equal to 0. So we need all of these to add together to figure out this one. So we have, let's start with CD. If we have 4/5 of CD, will bring us to CF. So we'll have 4/5 the forces acting on CD plus this one over here, 4/5 acting on CE plus 4/5 forces acting on CE plus the forces, so this one's pulling this way, this one's pulling that way, this one's pulling that way, plus the forces acting on BC. That is going to need to equal, so we have the forces pushing this way, we have the forces pulling this way, we have the forces pulling this way, must be equal to the force responding in this direction. That equals to 80 kilonewtons. So we could substitute a lot of these. So 4/5 FCD, no substitution. It is what it is. That's what we're trying to figure out. Plus 4/5 multiplied by, we know the forces acting in CE are, just gonna cross that off there, 5.57. And we know the forces acting in BC plus 4.45 is equal to 80 kilonewtons. All right, let's grab out that handy dandy calculator. All right, we simplify this expression. That's going to give us the forces acting on CD are going to be equal to 88.87 kilonewtons in compression. Compression, it's squishing together. It needs to help these ones, which are all pulling that way. In compression. All right, FCD, 88.87 kilonewtons in compression. Whoo, let's go. Okay. Let's finish off by doing, we have everything, but it might be worth it to just do some checks. If we figure out the last couple of joints. So let's take a look at the sum of the forces acting vertically equals 0. So if we look at the sum of the forces acting vertically, these should all add up to be the same, right? Totally. It equals each other. So we can now look at, so we know we have the forces acting on CF are equal to 50. So if we do instead for our CD, if we do 3/5 of FCD, that is going to equal 3/5 of FCE plus FCF. So this pushing this way should equal this pushing down and this pushing out in that direction. So we could substitute. We've got 3/5 of 88.87 is going to equal 3/5 of 5.57 plus 50. And if we get our calculator out, do the thing, that is going to give us 53.3. It's going to equal 53.3. Yeah, so we're golden. Everything matches up. Everything is equal. We're golden. If you would want to, you can also calculate all the things at point joint D. I'll let you do that on your own. That's a way you can just check to make sure that everything is exactly the same. But yeah, if we're writing these in, we can actually go up to this guy and start putting in what all of these members do. I'll let you do that on your own too. This video is almost an hour. Whew, tiring. But that's how you do the calculations. Take it easy, take it slow, be patient. What's the formula? The sum of the forces vertically equals 0. The sum of the forces horizontally equals 0. If you get to the point where you're stuck because you don't have the values, you maybe need to solve one before the other. So look at what the values you do have, put them in there, give it a go. Again, simple trigonometry. It's just a lot of things adding together. You're doing layers and layers and layers, and you do the same equation over and over and over again, and it becomes quite simple. And then you get to points for most of them, it's just equal and opposite, like EF to FD. It's like equal and opposite. CF to the force pulling down on F, equal and opposite. Yeah, so hope you enjoyed this video. I'll catch you in the next one. I might do a third problem. We'll see how it goes. All right, take care.